let's see if it works. Live demo is always fun, right? In a live audience. And I have many microservices, okay? I promise you, right? Yesterday I heard many talks against microservices. Today I will show you that microservices work and that it's not a big problem to spin them up in 30 seconds. So I have another fun fact. If I would have walked here, it would have taken me 460 hours to walk here, 2,223 kilometers. I'm super glad I took the plane because it was only 3 hours. I live close to Munich, south of Munich. My hometown is called Rosenheim, which is close to Austria. The company I work for is Coavia. We're a small software project house, independent project house. You know, we do cool projects with cool technology. I do most of my projects with that big car manufacturer that happens to, well, be in Munich, okay? The one with the 3 letters, German car manufacturer. Okay, well, I have a lot planned. That's the agenda, okay? And I will show you through that showcase. As you see, right, this is a tech conference, so we can have fun. I'm going to show you how to build beer services, okay? So I build a microservice that you can ask for different types of beer, right? I drink beer, lager, IPA, you name it. We start off with a small REST service with a good application, JSON REST interface. We learned yesterday, REST is all about pretty URLs and JSON, right? So we start off with that REST beer service. Then we're going to extend that beer service with a binary interface, with a protocol buffers interface to get rid of some of the, well, annoyances about JSON, right? JSON is nice and easily readable. Unfortunately, it's also pretty bloaty and not very efficient in terms of serialization. Once we've done that, we kick off our gRPC beer service. I will show you how to implement a gRPC API, and that is not a big deal to implement such APIs, okay? Because a lot will be generated, a lot of the code is generated, and it's rather simple. We do that in Java today, okay? Initially, I planned to show you a Quarkus demo, but after talking to Graham, I decided yesterday I will do the micronode today. Why? What the heck? I changed the demo yesterday. I can show you the Quarkus code anyway, right? Just to make it even bigger, the demo. And once we have that, I will show you how to connect to that beer service using different clients, using a CLI client, using a web client. I will show you how to, well, that one up there, the gRPC REST gateway, well, the fun part about gRPC and the ecosystem is that you don't have to write the REST interface, you can let it generate, okay? So that one up there is 50 lines of Go code. Then we have the REST interface again as a proxy towards our gRPC API. Small Nginx demo with the load balancing. And last but not least, I can show you, at least in code, how you can connect a TypeScript, you know, like an Angular application or like a React application. Also, let that one talk to your beer service. So a lot, okay? Quite a lot. Let's spin that stuff up. Where is, no, not here. We do that here. Tilt up. And then let's see if everything's going. Okay, so you see there's a lot of happening here now. Once that's spinning up here, everything that should take like 30 seconds, you see on the left-hand side, we have all the, you know, all the services. The envoy is already up, the gateway is already up, the Nginx is already up, the beer UI is already up, the beer service is already up, and the REST beer service is already up as well. Did that take 30 seconds? 30 seconds? Lots of microservices? 6? Right? This is how things should be. If you're interested in the code, have a look at that repository. Everything I will show you is here, okay? Copy it, clone it. So let's have a quick look at REST. Right? So what's so special or good about REST? So we come more or less to the first demo. So this is REST APIs, right? As we learned yesterday, pretty URLs plus JSON. That's REST. So you have verbs, you have get, post, get, put, delete. Well, you have then the pretty URLs, right? You talk about resources. Our resource here in that example is the beer. And Here on the right-hand side, you see what does the request look like. Okay, I want a specific beer. I have a nice, pretty URL. I specify accept application JSON, and I get back that response here with the content type application JSON. I got a nice formatted, JSON structure. Now, the big question is, what's wrong with REST? And in theory, I would say probably nothing. In practice, I would say usually quite a lot is wrong. Because those pretty URLs, they often don't look as pretty as this one here, right? You find strange verbs in the URL, for example, update shopping cart or something, where you say like, hey, didn't you understand REST, right? I've seen REST API in my lifetime when I do a bit of consultancy work. The REST payloads, because it should be readable, right? And what do you do with JSON to make it readable? Well, you transmit shitloads of, white space. 60 kilobytes of payload just to make it readable. It's not such a good idea, right? There is this Richardson REST maturity model that tries to give you let's say, some means of judging how good your REST API is. And I would say most of the REST APIs nowadays are somewhere between level 1 or 2. Either you have good resources, but you haven't understood how to use the verbs, or you use the verbs, but the URLs of the resources are pretty strange, right? Anyone ever implemented a hypermedia control type level 3 REST API? See? No one. So I think we can do better. These here? The 8 fallacies of distributed computing, also pretty old, right? They have a beard like that, right? I think 1994. So network is reliable. Well, we all know it isn't, right? Latency is 0. We all know there is latency, definitely. Bandwidth is infinite. Well, not really. And many, many more. And I highlighted those 3 that I want to stress a bit today: latency, bandwidth, and transport cost. Now, what's wrong with the REST APIs? Because you talk in resources, usually what you have to do, you don't do one call for the one resource. Usually you have that resource connected to other resources. So you have to do one call plus many, many other calls, right? With REST, it's usually that either you do underfetching, which is that in the case, because you underfetch the data, you need more data for complex use cases, you have to do more calls. More calls means more latency, added up latency, right? Same with the bandwidth, right? The more data you transmit, and yes, you can gzip, your JSON payload, and you probably should. And then you're right, it's already a bit smaller, but you can do better than that, even better. And the same is with transport costs. Transport cost is the cost or the time that takes you to marshal and unmarshal your data, right? From the wire to your object. And with JSON, unfortunately, most JSON mappers are not that fast, right? Jackson, JSON, whatever, they're all named, right? They do a good job, but they're not very fast usually. So let's improve on that. And protocol buffers, this is now time for the first demo already, is improving a lot on that, right? So that is protocol buffers on one slide. I'm not going to read everything through, but language neutral, platform neutral, extensible. So it's like JSON and XML, just smaller, faster, and easier, okay? So that's in a nutshell. It uses an interface definition language to define your structures and payloads, right? So it's a text file. The IDL file is a simple text file with a rather simple syntax, I'll show you in a second, that you use to define your message payloads, right? And it's fully typed. You have many types there, right? You have bytes, integers, doubles, floats, booleans, arrays, hash maps, lists, everything you would need to do proper type definition. It supports code generation. So from that IDL definition, you can then generate either your Java code, your Python code, Objective-C, Kotlin, Dart, C++, Go, Ruby, C#, you name it. And if there is not an official compiler, go out into the community. I'm sure you will find another compiler from someone in the community. The cool thing is that protocol buffer supports backwards and forwards compatibility, right? So if you have two systems communicate with each other with an independent release cycle, for example, right? You can have a server accepting new messages or adhering to the new version of your IDE of your API, But you could have, in theory, older clients sending old messages, and the server will still understand that, right? And the other way around, right? So old clients can also unmarshal new payloads or payloads that adhere to the new version of your API. And that is pretty good. Well, there are a few rules you have to stick to make that work. But as long as you adhere to those 3 rules here, this will work. Okay, so this is what protocol buffers looks like. Up there, you have a few options. Those options usually determine how the code generation works. So you have specific options for Go, for example. Here you see specific options for the Java world. You can tell it, hey, which package should my generated classes be in? You specify the outer class name. That is kind of a huge class that has many inner classes. And then you specify the message. You see a few strings, the float of the alcohol, a nested enum type, and that's pretty straightforward. And on the right-hand side, you see a bit of a few Java snippets. The first one is how you do marshalling. Okay, so once you have the code generator run, you usually use the builder of those types. So there you have the beer produce, the beer new builder, set as and set name, then you say build. That's your POJO, and then you say 2-byte array, and that's then a byte representation, and you send that over the wire. And to come back from the bytes, this is that one simple call here. Also, you need to invoke the Proto-C compiler. Now, we in the Java world, either we have a Gradle build or a Maven build, right? There are many plugins for that, so you don't have to explicitly specify the Proto-C command down here, so usually let your build tool do the magic. Okay, so let's do the first demo. So I said we have a nice REST API, and I told you, well, today the demo is using Micronaut. So here you go. So yesterday I went to the Micronaut site. They have a nice generator, and they have a CLI, which you can use, or Graham used Visual Studio Code yesterday, the plugins. I'm usually a CLI type fan, so use the CLI, generate this Micronaut application, everything set up. All you need to do is plug in that controller here, and you see this is my controller of my REST API. That's done. So now we want to improve on that one because we think, well, we want to communicate using binary payload. So what do? We add that beer proto definition here under source main proto. Then we need to go into our Gradle build file. All we need to do is, well, add that plugin here, up here. Can you all read that big enough? So we add the proto plugin to our Gradle build. We need the Protobuf Java dependency. That's this one here. Well, and down here, you invoke the compiler. That's pretty much it, okay? So now our Gradle build is enabled. It will generate the required classes from our proto file definition. I also found out that there already is also a Micronaut Protobuf support dependency to now take over when I want to send binary payloads over the wire using a standard HTTP 1.1 REST controller. So this is this one here, right? We make it even bigger, like that. So that controller here is similar to the REST one, only that now for the responses and the requests, I'm using the generated protocol files and classes. So this here is the get request been generated. This here is the get response, also the generated Java class. And all I need to do is I need to use that MIME type here, application X protobuf, to just tell it, hey, if that comes in, it's going to be a protobuf type or serialized request. Do the unmarshalling, do the marshalling. And that's it, okay? So it's super easy to swap out JSON and use protocol buffers instead as an efficient way of transmitting the data on the wire. Right? And hopefully in the backend, everything fired up. So we do HTTP get localhost API base. Let's see if everything's working. Whoop. Demo. Yes. So that's still the REST API. Now, there's one slight trade-off now, right? This is invoking the REST API. If you would invoke this proto endpoint, well, you would see binary data, right? So not readable anymore, but efficient. So for inter-service communication, I would say efficiency counts more than readability. So if you ask yourself, I'm always talking about efficiency. Well, let me say the disclaimer before, okay? So this is other people's benchmarks, right? This is not even my benchmark. So if you want reliable data or proof that your API is faster than before, well then please, do a load test, do your own benchmarks. Don't trust other people's benchmarks, right? Don't even trust me. But I think the figures speak for themselves, okay? So what did they do? So I think they did the prototype in, let's say, Spring Boot. Yeah, that was Spring Boot on a DigitalOcean server. That was the load test environment. So they did it in a non-compressed and in a compressed fashion. Okay, so compressed JSON versus uncompressed JSON. And as you see here, the marshalling and the unmarshalling is 5 times to 6 times faster if you go the protocol buffers route. Okay, and this is significant, guys, right? I mean, is it 150 milliseconds or is it 25 milliseconds, right? In a high-performance environment, microservices serving 800 requests per second, this does matter, I think, right? And if you have to make more calls, that matters even more. All right, so we dump REST for a bit. Let's do gRPC implementation. So gRPC in a nutshell, modern high-performance open source framework, universal RPC framework. Now here come the big differences. First up, gRPC uses HTTP2 as transport protocol. Okay, multiplexing, TLS, compression, modern HTTP protocol, right? So for its different types of communication, so you have the classic request response, obviously, but it gets even cooler. You can do streaming, client-side, server-side, bidirectional, unidirectional. gRPC uses protocol buffers as the payload format, okay? And you also have to use the interface definition language to specify your gRPC APIs. You have various options on load balancing, proxy, client-side, looker-side, tracing, health checks, authentication can be plugged in. Very nice. The client as well as the server code can be generated from the IDL, using for all those languages I told you previously. And gRPC is more than just the API. It also has an ecosystem of different other sub-projects, namely the gRPC gateway and gRPC web. So the gateway is the stuff I'm going to show you later, how you can annotate your IDL with a few options to then let those generators here generate a matching REST proxy for you. And the web stuff is basically to let JavaScript clients communicate via the gRPC text protocol with your gRPC service. So this is what a service definition looks like. So you have the beer service, you have different RPC methods, all beers, no parameters, empty, returns the response, and so forth. So I think you get the point of that API. So we come back to the demo. Again, yesterday I decided, I implement that in Micronaut. So either go to, the web page, this generator, there's a specific options that lets you already generate a skeleton for a gRPC application. You can do the same on the command line. This is exactly what I did. This is pretty much what I got out of it. Again, you specify the proto definition. This is what I just showed you. Up here are a few more options now, but basically the service beer service is the stuff I've added. The messages are exactly the same messages as before. This time the build is already, enabled. So you see here, that one here changed a bit now because the relevant part is this here. In addition to the Protobuf generation, I need to tell the plugin, hey, please use the gRPC plugin to generate even more code. So once that's done, well, all I have to do is implement, give me a second to make that a bit more readable. Implement one class that contains my business logic. This class needs to extend from that base class here, right? This one has been generated. And all I need to do is I need to override the method stubs and provide the actual implementation to return a list of beer, or to find one single beer based on the request, or to create one, or to update one, or to delete one. Okay? So super simple, super straightforward, plain Java code, not very technical code in my opinion. So this is the real business code already. And the plumbing for the gRPC, this is all hidden from us developers. This is all generated for us. So if I want to invoke that one now, well, either we could use, a Java client and a test. This is what the test would look like. Well, this is actually the application test, right? But using that that interface here from that class, basically this is what you can then use to invoke the methods on the remote application. What you can also do is, well, there is a command line tool available, which is called gRPC curl, right? I invoke that one. You see, that's the host here, localhost 109090. So that is my small Kubernetes cluster I'm using there. Wait. Wrong directory. Okay. Wait. Ta-ta. Ooh. The server always does not expose. Why? Well, it worked yesterday. It works on my machine. Well, wait. It should work. gRPC peer service. Okay, started. Well, I have a web UI, and well, give me a second. Well, it's always good to be prepared to have a different demo. Open, then gRPC beer service port 1990. Let's see, connect, choose beer, choose method, all beers, submit. I don't know why it's not working on the console. With my web client, it is working. Okay, so this is a nice fancy web UI you can use to to make gRPC calls. As you see here, this is the in-cluster connection to my beer service. I specified in the proto file, and if I invoke that one here, I get the list of beers. If I choose, oh no, not the create, I want the get beer. Hop, I specify that one here. I submit, right? I get one response. So it is working. I don't know why it's not working on the. That port up there is just a port for for the web UI. It's not the gRPC port, right? And the port of the service is that one here, which is the 9090, but that's the cluster internal port. Well, we can give it one more go. I don't understand. gRPC curl plain text. Oh, here we have the same issue again. Yeah. But that is the the forwarded port. Good question. We will solve that later because we're running out of time. But it is definitely working, as you saw in the in that part here, right? So only the external connection doesn't seem to work for now. Anyhow, so back to the slides, right? So apart from that minor glitch that we couldn't call it on the command line, we have now implemented the beer service, right? A lot of code has been generated, and it was pretty straightforward to then, extend from the base class and to go further. Now let's have a look at other fancy options we have. I told you gRPC uses HTTP 2. So what you would need, if you have multiple instances of those and you want to do load balancing, then you also need to have a load balancer that can do load balancing on HTTP 2 so that you can make use of the multiplexing of that connection. Nginx can take over that one. Next thing, well, now we have a binary interface, right? What if our clients out there are not that far yet, are not that modern yet? What if we have clients out there that can talk REST? What do we do then, right? This is what the gRPC REST gateway is for. And what if we have web clients out there, fancy web UIs, Angular, React, whatever, right? What was it yesterday? Gatsby, maybe. So let's have a look at that. Now, what I can do with the interface definition language is now, with a few options, annotate my gRPC methods and now provide it with a relevant mapping of how do you map incoming HTTP 1.1 requests to gRPC requests, and the other way around. How do I map gRPC responses to HTTP 1.1 REST responses? And this is the annotations you see here, for example. So up there, I say the allBeer method that maps to a GET request on the following URL. The getBeer maps to API/beers. You see here that placeholder. So take that string from the URL and map that to the ASIN field of my request, right? And the response body is the beer field of my gRPC getBeer response. And take that one, marshal it to JSON, and output that one, right? So it's a few annotations that you have to specify here to then let, well, the magic happen and let, the proto compiler compile the required files for this. Now there is one slight downer maybe for the Java community. The code that's now generated, it does not work with Java. So they do not have a Java version for that one, for the gateway. So you would have to write a bit of Go code, but I promise you 50 lines, okay? Not that much. So I use two tools. The one is called Buff. And for the ones who have been in my workshop on Wednesday, this is what we exactly did. So this is a small CLI tool you have to install. You install that on a command line. You have to insert this dependency here, and then I tell Buff to generate the required gRPC gateway code. This is basically here the generated Go code. So if you are able to read Go, then that is what you have to do. And then, and this is actually the only thing you have to write manually, this is 55 lines of Go code. This is more or less the small server main, Go main service to then fire up the REST gateway. So we have a REST endpoint on the outside, and that thing will then translate the REST call, the HTTP 1.1 call, as I told you before, towards the gRPC call and forward it to our internal service, right? And the proto file for that one, where is it? Here it is. Boom. Right? So here you see now all those options specified. Delete request, put request, post request for create, the get request, the stuff I just showed you on the slide. And that's pretty much it. So if I now do HTTP localhost, oh no, HTTP get localhost. So what's the port? 108090, I think. Hopefully, yep. And I will show you, wait. We do that here, okay. HTTP get localhost 108090, right? Up there, you see that the all-bs gRPC API has been called, right? So I talk to my gateway now, but internally the gateway talks to my Micronaut gRPC interface. So if I want to do that, slash that one here, that should be the getBeers code, and so on and so forth, right? So with a bit of Go code, I was now able to serve both worlds, right? Have high efficient internal gRPC communication, and for those legacy clients, well, vintage clients, whatever, REST clients, right? I can serve them also. I wanted to show you the Nginx load balancer. That's also rather simple, right? So this here is, I specify the upstream server, so they both live in my small Kubernetes cluster, and all you have to do here is specify the server, listen on the following port, listen on 4x8, HTTP 2, and for the location beer/beer service, please forward everything and do a gRPC bypass, right? So with a bit of Nginx configuration, load balancer implemented, done, right? Bit of Docker file, copy in the conf file, and you have a perfect Nginx load balancer for your gRPC services. So not a big deal to implement, load balancing proxies. Now for the gRPC web stuff, well, it gets a bit complicated, and it's a very young project still, okay? So what you need for web clients to connect to your gRPC server, again, you need a proxy before your gRPC service that does the translation of the gRPC text protocol towards the binary gRPC protocol. The proxy they have chosen to do that is an Envoy proxy. So if you're a bit in a cloud native universe, Envoy is a known, sidecar container, often used in many service meshes, but you can use it standalone as well. Again, configuration pretty similar to the Nginx demo. And the magic line is more or less that here. There is a specific Envoy filter available that does the translation for you, right? So same here. Write a bit of YAML code, 50 lines. That's the config for Envoy. Stick that one in your Docker container, configure it, deploy it. That's done. And on the JavaScript side now, right? Again, you take the proto definition. That is the proto definition as before. I use this buff tool again to let buff generate or invoke the protocol compilers to generate JavaScript code this time, or JavaScript and TypeScript code this time. This is what's done here. I say, okay, specify or generate JavaScript, and here generate the gRPC web relevant code, this technical code using the gRPC text protocol. That's back there here. This will then, generate those files here. I'm not a big JavaScript guy, right? This is usually my younger colleagues that do that. But that's the, the TypeScript and the JavaScript code that comes out. And that one here is then the JavaScript code that you can use to interact with your service, right? So you have a generated JavaScript beer service client. You have to give it the port and the host. Where does my Envoy proxy live, right? And then here, you invoke the all beer methods, for example. Or here down here, you invoke the beer request. Since I have a few minutes left, well, let's try that out. So we have to open a file. We have to go into the directory. Somewhere here is my index.html. Open, right? Ooh, where do I open the developer console? How is that done in Chrome? I need help. Where are the developer tools? Back here somewhere, right? Tools. Yes, here we go. right? So down here, and you see, this is the console. So when that thing loads up, it's already, making the calls, right? So here, I've already done the call towards my thing. Maybe if we do a shift reload, right? It's already outputting the beer that's done the call towards my service. So here, look here, all beer is called, get beer is called. So that is basically what it's doing. So here, right? I invoke that a few more times. You see here, the calls from my JavaScript client now ended up here in my Micronode gRPC service via the Envoy proxy, right? So the JavaScript code talks to the Envoy proxy does the translation and forwards it to my backend service. All right, so we have JavaScript talking to gRPC. We have REST clients that are able to talk to gRPC. We have efficient internal communication via gRPC. So if you have service-to-service communication, my advice would be consider gRPC, right? It's a complete ecosystem. So to sum things up, I think gRPC rocks. If you want the best proof of concept, why that is a good idea, have a look at Kubernetes. You talk to a Kubernetes cluster from the outside using REST. Internal, everything is gRPC, super high performant. I think this is the future for modern inter-service communication. Thanks, guys.
Thank you very much. Maybe someone have any questions?
Hello. First of all, thank you for the talk. I got one question because I already worked with gRPC before, but only just as you said, between internal communication. But there's one question, and it's about because the problem that I have in the past is we have to use the same file for the communication. Is there any way or any library that's using the same file for the same communication? Because we already know, I mean, we are the same developer for the same services.
Yeah.
So it's a problem that we have to duplicate the proto.
No, this is, okay, well, that is an awesome question, thanks. This is just for demo purposes to show you the evolution of the proto file, right? What you would use or do in reality, have a dedicated API project where the proto file is in, where the generator is in, let the generator generate the Java code, compile it into a normal jar file, put the proto file plus the classes into the jar file, put it into some Nexus repository, and within your services, then do make a dependency on the generated code, so you only do that once. This is how I would do it in practice.
So you have one project when you create the service and the client,
yeah,
and then you import whatever you want to use it as a service or as a client.
Exactly. So then you make sure that you always use the same proto definition.
Okay.
If that is not possible, there are cool tools out there that let you lock the proto definition. There's a project called Protolock that then will kind of version the proto definition and at least tell you, hey, listen, the service you're talking to or the client that is using this one is not compatible anymore. So you can check for compatibility at compile and build time, for example. So that is pretty cool also. But as I said, if you have full control of client and server, put it in a dedicated artifact, version that one, put it in a Nexus and use a dependency.
Okay. Thank you so much.
Great. Anyone else?
Up front here, there's a young man.
Well.
Thank you. May I ask, GraphQL versus gRPC? Is it mainly about flexibility versus performance?
Also, great question. Thanks. But first up, I think in technology we should stop about talking always about versus. It's usually not versus; it's together, right? GraphQL plus gRPC, great combination. gRPC in the background, GraphQL at the front, have a GraphQL gateway to enable GraphQL clients to specify, right, which data do I need, and then let the GraphQL gateway talk to all those gRPC backend services and aggregate the data. So use it in combination, not vice versa, right? And most GraphQL gateways like Apollo, or have a look at the Glue API gateway. That's a cloud native API gateway. That is a dedicated infrastructure component that can already do exactly that, right? GraphQL on the outside, gRPC backend calls.
So thank you very much for nice questions, great answers, and see you soon.
Thanks so much.